Good morning, class. Welcome to another online lesson here. Today we'll actually be closing out the first section of Chapter 9, where we've been working with the scale factors and the relationship between linear scale factors, area scale factors, and volume scale factors. Today's lesson actually takes us through some real-world situations, relying on our knowledge of area and volume scale factors and how they work to be able to come up with some different amounts of paint or weights or things, how much tanks can hold, all using what we know about scale factors. So your job today is to do just these three problems in the lesson, 53, 54, and 55. And then once you get through with those, come back and we'll talk about a couple of the key points. There won't necessarily be new ideas introduced. You'll just be tasked with using what we've already been working on to actually solve these problems. So at this point, please pause the video, work the problems on your own paper, and once you've finished, return here for a quick recap. All right, guys, good luck. And welcome back, guys. So hopefully that lesson went okay. You did have the answer key also linked on Google Classroom, so you could check your work as you went. But just a quick run through with me to make sure you picked up the key ideas. So in 953, you had to use what you knew about the relationship between areas of similar figures to think about the paint that was coating. So hopefully you relied on the fact that for the area, you take your linear scale factor and square it to be able to work there. For the weight of the statues, you had to rely on the volume relationship, and so that would require cubing the linear scale factor to be able to do so. In 54, where we were working with these jumbo storage tanks, they gave you dimensions that were 4/5 the size of a similarly shaped model, and that ratio was the one that you would use to work with the different capacities here for those tanks. 55 is one I'd like to take just a minute to break down because it builds off a problem we had previously done way back in chapter 7, where we built those paper tetrahedra in our class, and then you and your teammates tried to stack them together. Well, they've given us an example here where the large clear one is actually twice the dimensions of the shaded small one on the top, and that was all we're really told, but that's enough to be able to work with this figure. So in part A, where they say if the volume of the large one is 138 inches cubed, find the volume of the small shaded one. Well, that just relies on our knowledge of scale factors. So if we know the volume of the large is 138 cubic inches, and the small one has dimensions that are linearly half the size, well, that means that we take that scale factor of 2 from small to large, and we cube it to work with volumes. So 8 multiplied by the volume of the small figure is going to give us the volume of the large one. From there, we can just divide by 8. When we divide 138 by 8, let's get our calculator. So we get 17.25. So our first one, for A, you should have had 17.25 cubic inches for the volume of that small tetrahedron. For part B, this was an interesting one because it actually takes us back and lets us use some of those triangle shortcuts that we've accumulated throughout the year. So we're told each face of a tetrahedron is an equilateral triangle. If the small shaded tetrahedron has an edge length of 16 centimeters, find the total surface area for each of the tetrahedra. So I actually went ahead and drew that triangle ahead of time. That's what's at the top of this page. And you can see it's got the 16-inch edge length. And so that could be marked on each side. And it's also an equilateral triangle, which we know has 60-degree angles in the corners. I went ahead and drew the height in here. And by doing that, I essentially created two 30, 60, 90 right triangles. If we look at the one on the left, we can see it'll have a hypotenuse of 16, a shortest side of 8 inches because that's half the 16, and then using our shortcut we know the height will be 8 radical 3, or 8 times the square root of 3 inches. All of a sudden, that's what we need to get the area. So if I want to get the area of that full equilateral triangle, I can take half the base, which is 8 inches, multiplied by the height, which is 8 radical 3 inches, and I see the area of one triangle is 64 radical 3 square inches. So that's one of the faces of a tetrahedra. If I were to get the smallest tetrahedron's total surface area, I know there are 4 faces, so it would be 4 multiplied by 64 radical 3, which gives us 256 radical 3 square inches for that surface area. If I want the surface area of the largest one, well, we know that the relationship between the surface areas is the scale factor squared. The scale factor between those was 2, so if we square it, it'll end up being 4 multiplied by 256 radical 3 inches squared. And when we actually do that math, we'll get 1024 radical 3 inches squared for the largest tetrahedron and its surface area. So that's an application using scale factors. For the final part, we're given an incomplete tetrahedron that was created using 4 small ones, which we can assume still have that scale factor of 2 to the large one. And now we're told that the volume of each small one is 50 cubic inches, and that's enough to find the volume of the gap. Because if a small one has a volume of 50 cubic inches, to get the volume of the large, we take the scale factor of 2 and we cube it to get 8, and 8 times 50 is 400 cubic inches. So the total volume of the large one is 400 cubic inches. I can see 4 small tetrahedra, which each have a volume of 50 cubic inches, so that means there's 200 cubic inches there. Taking the difference of 400 minus 200, we see that that incomplete gap has an area, or a volume, of 200 cubic inches, because that was the difference between what we would expect the full volume to be using the scale factor and what we know the volume is, because we have 4 of those shaded tetrahedra. So that's another application of how we can use those scale factors. Hopefully by the end of this lesson, you are feeling pretty comfortable using these ratios of similarity. The math notes give you one last look at how we can work with linear, 2-dimensional and 3-dimensional scale factors. So please take a read through that. And then your assignment today is to complete the review and preview and take a picture of that to upload to Google Classroom. Just like last week, I'll be offering office hours from 9 to 11 each day, so please be sure to email questions or ask them on Google Classroom during that time, and I'll get you prompt answers. Good luck with this assignment, and I'll see you guys